Welcome to this episode of Mentors at Your Benchside, the podcast giving you advice, tips and tools for getting the most out of your research. I'm Adam Paulson, and today I'll be talking to you about the metrics involved in measuring scientific performance, focusing on the H-index. So how do you measure how good you are as a scientist? How would you compare the impact of two scientists in a particular field? And what if you had to decide which one would get a grant? One method is the H-index, which I'll discuss in more detail. First, I'll touch on why this is not a simple task. Measuring scientific performance is both more complicated and more important than it might seem at first. Various methods for measurement and comparison have been proposed, but none of them are perfect. At first, you might think that the method for measuring scientific performance doesn't concern you, because all you care about is doing the best research you can. However, you should care because these metrics are increasingly used by funding bodies and employers to allocate grants and jobs, so your perceived scientific performance score could seriously affect your career. What are the methods involved in measuring scientific performance? The methods that might spring to mind first are recommendations from peers. At first glance, this might seem like a good idea in principle. However, it is subject to human nature, so perceived performance will inevitably be affected by personal relationships. Also, if a lesser-known scientist publishes a groundbreaking paper, then they would likely get less recognition than if the same paper was published by a more eminent colleague. The next method is a measure of the number of articles published. A long list of publications looks good on your CV, but the number of articles published gives no indication of their impact on the field. Having a few publications that have been well heeded by colleagues in the field, that is, they are cited often, is better than having a long list of publications cited poorly or not at all. Then there is the average number of citations per article published. So if it's citations we're interested in, then surely the average number of citations per article is a better number to look at. Well, not really. The average number could be skewed greatly by one highly cited article, so it does not allow a good comparison of overall performance. That brings us to the H-index. In 2005, George E. Hirsch of the University of California at San Diego published a paper in PNAS in which he put forward the H-index as a metric for measuring and comparing the overall scientific productivity of individual scientists. There's a link to his article in the episode description. The H-index has been quickly adopted as the metric of choice for many committees and funding bodies. Conceptually, the H-index is pretty simple. You just plot the number of papers versus the number of citations you or someone else have received. Basically, H equals the number of papers that have received at least 8 citations. There's a nice graph that demonstrates this in the published version of this article, and there's a link to this in the episode description. So if you have an H-index of 20, then that means you have 20 papers with at least 20 citations. It also means that you're doing pretty well with your science. The advantage of the H-index is that it combines productivity, that is the number of papers produced, and impact, the number of citations, in a single number. So both productivity and impact are required for a high H-index. Neither a few highly cited papers nor a long list of papers with only a handful of citations will yield a high H-index. So what is a good H-index? Hirsch reckons that after 20 years of research, an H-index of 20 is good, 40 is outstanding, and 60 is truly exceptional. In his paper, Hirsch shows that successful scientists do indeed have high H-indices. 84% of Nobel Prize winners in physics, for example, had an H-index of at least 30. But what are the limitations of the H-index? Although having a single number that measures scientific performance is attractive, the H-index is only a rough indicator of scientific performance and should only be considered as such. Hirsch himself writes, "Obviously, a single number can never give more than a rough approximation to an individual's multifaceted profile, and many other factors should be considered in combination in evaluating an individual. This and the fact that there can always be exceptions to the rule should be kept in mind, especially in life-changing decisions such as the granting or denying of tenure." The limitations of the H-index include the following. It does not take into account the number of authors on a paper. A scientist who's the sole author of a paper with 100 citations should be given more credit than one who is on a similarly cited paper with 10 co-authors. It also penalizes early career scientists. Outstanding scientists with only a small number of publications cannot have a high H-index, even if all those publications are groundbreaking and highly cited. For example, and I quote, "If Albert Einstein died in early 1906, then his H-index would be stuck at 4 or 5, despite him being widely acknowledged as one of the most important physicists, even considering only his publications to that date." Another limitation is that review articles have a greater impact on the H-index than original papers, since they are generally cited more often. Lastly, the use of the H-index is now broadened beyond science. However, it's difficult to compare fields and disciplines directly, so really, a good H-index is impossible to define. There are several online resources and H-index calculators for obtaining a scientist's H-index. The most established are the ISI Web of Knowledge and Scopus, both of which require a subscription, probably via your institution. But there are free options too, one of which is Publish or Perish. If you check your own or someone else's H-index with each of these databases, you might get a different value. This is because each uses a different database to count the total publications and citations. ISI and Scopus use their own databases, and Publish or Perish uses Google Scholar. Each database has different coverage, so will come up with a different H-index value. For example, ISI has good coverage of journal publications but poor coverage of conferences, while Scopus covers conferences better but has poor journal coverage pre-1992. There's a link to more about Publish or Perish and an article comparing the online resources that calculate the H-index in the episode description. So let's sum up the H-index. The H-index provides a useful metric for scientific performance, but only when viewed in the context of other factors. So when making decisions that are important to you, like funding, a job, or finding a PI, be sure to read through publication lists, talk to other scientists and students and peers, and take account of career stage. Keep in mind that an H-index is only one consideration amongst many, and you should definitely know your H-index, but remember that it doesn't define you or anyone else as a scientist. So that's it for this episode on the H-index as a useful metric for scientific performance, along with all the caveats. Check out the episode description for links to related articles and resources, and don't forget to subscribe to the podcast to get more help and advice from mentors at your bench side.